Hello everyone and welcome to this lecture. In our past lectures we dealt with only first order equations, but from now on we will be dealing with higher order equation. To begin with, I would like to discuss second order ordinary differential equation. So an ordinary differential equation of second order has a general form like the following. Let's say a y double prime of t. This double prime means it's a second derivative with respect to t. Then by prime of t plus cy of t is equals to some function of t. This is the most general form. Now, the equation can be called homogeneous if f of t equals to 0, and it's non-homogeneous if f of t is not equals to 0. And this can be even a constant number as well. It might not depend at t at all. So those will fall into the category of non-homogeneous equation. And if your f of t is 0, then that means that's a homogeneous equation. So first we would like to deal with this homogeneous equation, and then we'll focus on non-homogeneous equation. And also I would like to emphasize that this a, b, c, they belong to the set of real numbers. But before we dive into how to solve second order ODE, let's just talk about some prerequisites. And one of the key concepts is the Wronskian of some functions. So let me just define the Wronskian for you. It's called W-R-O-N K Wronskian. Sorry, I think I made a mistake writing the name. It should be like this, Wronskian. So let's say you have two functions f1 of t and f2 of t, and the Wronskian for these two functions will be defined by f1 f2. This t over here means the Wronskian is dependent on t, and this is just the determinant of the matrix f1 of t, f2 of t, f1 prime, that means the first derivative, and then f2 prime. This is equivalent. This is equal to the determinant of this thing. So if you write it more explicitly, this is just f1 f2 prime minus f2 f1 prime. And notice that I haven't written the t dependence explicitly. It is understood from the context. So why is this Wronskian useful? Because Wronskian tells us about the linear independency or linear dependency of two different functions. So Wronskian tells us about linear dependence of f1 and f2. In fact, you can go on and generalize this for many functions, where let's say you have n functions and you want to see whether they're independent of each other or not. You can even do that, but this will not be needed for now, and when it will be needed, I'll discuss that with you guys. So if f1 and f2 are linearly dependent, so let me just write it again. If f1 and f2 are linearly dependent, then one of them can be written as a scalar multiple of the other, right? So let's say this f2 will be some alpha f1, if they are linearly dependent. And now if you use this fact and compute the Wronskian, you can see that the Wronskian will be 0, because the Wronskian was of f1 and f2. This was in general f1 f2 prime minus f1 prime f2, right? And if you use this formula over here, that is this relation, this will be alpha, and you will have f1 times f1 prime minus f1 prime times f1, which is just 0. So if two functions have the Wronskian 0, then they are linearly dependent. So if Wronskian of f1 f2 of t is 0, we can say that f1 and f2 are linearly dependent. And if this is not 0, that is the Wronskian of f1 f2t not 0, that would mean f1 and f2 are linearly independent. Now this will be useful because the equation you see over here, we will want to have linearly independent solutions. And first we are going to see how we can do for this homogeneous part, and secondly we will see how we can do it for a non-homogeneous part. So let us start with the homogeneous equations. So homogeneous second order ODEs, and this will have the following form, right? And we want two linearly independent solutions. So let's write that we want two linearly independent solutions, and then we will combine them to get the full general solution. And note that this combination is also a linear combination to get the full solution. Now let's say you have some solutions. Let's say y1 and y2, they satisfy equation 1. So if you just put y and y2 over here, you can see that this equation will satisfy. That's what we are assuming, right? But we want to write the general solution, can be written as some arbitrary constant c1, y1 and c2, y2. And if you put this thing, let's call it 3, into 1, you will see that this will decouple. And so since y1 and y2 are solutions of this equation of 1, it turns out that their linear combination will also be a solution of 1. All you need to do, you just need to put this thing over here into 1 and differentiate. So these are some things that will be useful. Now we want to see what are the forms of this y1 and y2 take. Notice that this equation over here, let me just use another color, that is the equation over here, indicates us to find some y that when differentiated, it retains its shape. because the first derivative, the second derivative, and the function itself, they are a linear combination of each other. So that's where this idea comes from. That is, we want to retain the shape of this equation, and a possible candidate can be e to the power rt, because if you differentiate it first one time, this is just r e to the power rt, which is proportion of which is just ry, right? And if you differentiate this thing again, that is this one, this will be y double prime, and you have ry prime, right? So stuffs like this. So this motivates us towards finding our solutions in terms of the exponential solution. So these are the things you have to put over there. So let's try to see what happens if you put this y equals to e to the power rt, a trial function, into the differential equation. The reason I'm calling it trial, because most of the time the functions you will try, it might not even give you a solution. So that's why they are called trial functions, because you are just trying to solve the equation with them. So we are saying this y should be in the form of e to the power rt. Obviously this r is also a real number, but it might be complex as well. So let's keep r in general. So r is something, r can in general belong to the complex number as well. So this is the safest route, but you will see that whether r is real or complex will come from some algebraic equation. And so let's recall our equation. That was a y double prime plus b y prime plus c y equals to 0, and we want to put y equals to e to the power rt into here. So if you do that, this will be ar squared plus b r plus c, and there you will have this e to the power rt equals to 0. But if e to the power rt is 0, that is, if e to the power rt is equals to 0, that means y is 0, and this is called a trivial solution. To get the non-trivial part, the non-trivial solutions, what you need to do now is you have to write, ar square plus br plus c equals to 0, and this is sometimes called a characteristic equation or auxiliary equation. I would like to call it auxiliary equation, or you can also call it characteristic equation. Now this is a second order equation, right? And we want to solve for r, and the solution is just minus b plus minus b square minus 4ac divided by 2a. So you can see that I have two roots for r, that is, r is now r1 and r2. These are the two roots. Let's call r1 as minus b plus, just plus over here, b square minus 4ac divided by 2a, and then you can call r2 as minus b square minus 4ac divided by 2a. And now you can construct your y1. Let's say y1 is now corresponding to the first root, that is r1, so y1 will be e to the power r1t, and y2 would be e to the power r2t, and finally y will be c1 y1 plus c2 y2, right? And you can write just c1 e to the power r1t and c2 e to the power r2t, where c1 and c2 are arbitrary constants, and this is the most general solution of a second order homogeneous ordinary differential equation. And there might arise different cases due to this R1 and R2, because you see, if b square is greater than b square is greater than minus 4ac, that means you have two real roots and they are distinct. And if you have b square is equal to minus 4ac, that means when b square minus 4ac is greater than 0, that means R1 and R2 is not equal to each other and they are also real. At the same time, if b square is equals to 4ac, that means R1 and R2 are equal. And if b square minus 4ac is less than 0, that means the roots are now complex. And in the next video, we will see how you can deal with this different kind of roots and construct the solutions. And we will also see some examples. Thank you.